Welcome to the video. The problem we're looking at here has two parts, so let's go through them one by one. So here's part A, let's say. Get the pen ready. Here's part A. Find the probability that a single randomly selected value is greater than 92.1. And here it is in probability notation. Here's the given information. The population of values has a normal distribution, so that's going to be key information, with mean 82.1 and standard deviation 63.8. And we're intended to draw a sample of size n equals 79 from that population. But notice for part A, we're just drawing a single value, so we're not going to need that number n for part A. We're just going to be thinking about a single value. So to answer part A, we can think back to some of the ideas of chapter 3, where we learned about normal distributions, and the ideas of chapter 10, where we learned about how to connect probability to the area under a curve. And let's begin part A by making a sketch of the normal curve we're dealing with. So it's a normal curve with mean 82.1, standard deviation 63.8. We can draw that curve out, so there's our horizontal axis. Make your nice symmetric bell-shaped normal curve, and at the middle, that value coming through the middle, 82.1. And then the value of interest here is that 92.1. We can think about where would that fall. Well, our standard deviation is 63.8, so out at this inflection point here, it would be 82.1 plus 63.8, pretty big number, you know, close to 150 there. So we get 92.1, going to be very close to 82.1, but let's just, you know, give a little space so we can see it. Getting crowded there, I'm just going to draw around it and say here's 92.1. And we want the probability that x is greater than 92.1, so if we shade in the area of interest, it's going to be everything above 92.1. Now this problem is almost identical to a problem we would have answered in chapter 3, except for instead of asking here for the area, the size of that area, they're asking for the probability that an observation would be in the range described by that area. In chapter 10, we learned that the probability can be found by calculating this area, so we need to know this area. So when we have a normal curve, and we're talking about finding the area of a normal curve, the command that's very helpful for us, we want to remember to use, is that norm CDF command. So we can use norm CDF here. When you use the norm CDF command, you look at the value of area of interest, and first you enter the left-hand bound. So the thing we'll enter here is 92.1. Then you enter the right-hand bound. Well, this area goes forever to infinity, so we'll enter 1E9. Then you enter the mean of your distribution, so in this case 82.1, and then the standard deviation, 63.8. I'm running out of space there, but there you go. Let's go ahead and put that in the calculator. So we're going to do second vars. Oh, I'm sorry, we're going to do stat. No, we're going to do second vars, sorry, and there it is, normal CDF, command 2. I wrote norm CDF, but on your calculator, it'll say normal CDF. It's the same one. Normal CDF. We enter that up and we put in 92.1, 1E9 with commas in between, then 82.1, comma, 63.8. And the answer we get when we do all that, what it comes out to be, is 0.4377. So this area is 0.4377, or almost 44% of the total area under the curve. So the probability of having an observation 92.1 or greater would be 0.4377. Alright, so now let's take a look at the second part of this problem and see how it changes. So here we'll say it's part B. In part B, now instead of asking about a single random variable, they're asking for the probability that the sample mean is greater than 92.1. So the value of interest has not changed, but the random variable has. The random variable has changed from being a single observation to the mean of a group of observations. So here's where we need to pull in the key fact we've learned in chapter 11, which is that when we're thinking about the distribution of a sample mean, it will be normal with the same mean mu as the population. What will be different is the standard deviation. So the standard deviation of the distribution of the sample mean will not be the population standard deviation. It will be the population standard deviation divided by the square root of the sample size. So it'll be here 63.8 divided by square root 79. And in general, when I do these calculations, I avoid doing that out and turning it into a decimal, because when I do that out and turn it into a decimal, I'm going to have to round, and that rounding may cause problems later on down the line and cause my other answers to be off by a little bit. So I'll just leave it right like that. Alright, so now let's draw a picture to explain this answer. I'm going to scroll down to give us a little more room to work with. Okay. Let me draw the picture for this situation. So we again, here's our, oh, pen doesn't want to write. Let's try again. We've got our horizontal axis, our normal curve, our mean, still at 82.1. The value of interest, 92.1. is still our value of interest, but our standard deviation has changed. So when we write this out, it's 82.1. My standard deviation, 63.8 over square root of 79. I'm not going to write it for my calculation, but just to get some intuition, let's do out what that is. So my standard deviation has now dropped to close to 7. If I do this out as a decimal, I get 7. We could round to 7.18. So my standard deviation is 7.18. So now if I think about where that inflection point is, it's 82 plus 7, it's 89. So the value of interest, 92.1, is more than 1 standard deviation away from the mean for this curve. So notice that our scale of the picture, even though the shape of the picture is the same in both cases, the scale of the picture has changed. Really, if you wanted to think about what's happening here, we wanted to draw, if this was my first normal curve with the standard deviation 63.8, when the standard deviation decreases, my normal curve is getting taller and skinnier there. Should still be symmetric, but taller and skinnier, so that when we were at 92.1 before, you know, we might have been there. Now we're out in the tail here if we say that was 92.1. So returning to our picture, we still want the probability that the mean is greater than 92.1, so we're looking for this area right here, and our calculator command to find this area is the same one as before. It's going to be normal CDF, and our input is going to be almost the same. The left-hand boundary is still 92.1. The right-hand boundary is still infinity. The mean is still 82.1, but the standard deviation has changed from 63.8 to 7.18 approximately, but I don't want to put 7.18 in my calculator because that's a rounded number. It's going to cause this answer to be off a little bit. I want to put in that calculation directly, and I can do that on the calculator. I can say 63.8 divided by, put that right in there, square root of 79, then close that parenthesis, and that will give me a more exact answer from the calculator. So let's do that. Second vars, option 2, normal CDF, and then 92.1, comma, 1E9, comma, 82.1, comma, and then 63.8 divided by the square root of 79, and I'm getting 0.0817, which would round to 0.0818. So it's going to be here, 0.0818, and that would be my answer. If we take a minute and compare those answers, notice what's happening here. Our population had a standard deviation, our population had a mean of 82, and we wanted to know what's the probability that a random value would be 10 units above the standard deviation. And we saw that's going to happen about 43% of the time. And then we said, well, now I'm going to take 79 random observations and average them. What's the probability that average will be above 92? And the probability dropped to less than 10%. We can think about why that is. If you're averaging a lot of observations, and we want that average to come out 10 units bigger than the mean, that means that most of those observations have to be quite a bit bigger than the mean in order to pull the average up that high, and it's unlikely to see a whole lot of extreme observations. We might see, 1 or 2 at random, but to see a whole lot would be less likely. So to get a mean a sample mean 10 units above the population mean, that's only going to happen about 8% of the time for a distribution with these parameters. All right, I hope that was helpful.